Okay, Unit 4 begins with Section 8.1, which is on growth and decay. We're going to need to learn how to graph and to recognize the equations and what you can tell just from looking at the equation. My pen is stuck. Turn this off and on, excuse me. Okay, all right, there we go. An equation y equals a times b to the x is an exponential function where b is a positive number other than 1. The b value is your growth factor. And then we'll talk about what a is in a minute. Well, I guess I could say it actually gives you the y-intercept. It's like the starting spot. Now, a is positive in this case, and b is greater than 0, then greater than 1. Then we're going to have exponential growth. Notice that x is an exponent in these equations. So unlike anything we looked at in the polynomial chapter, it's not a polynomial function. Y increases as x increases, and the graph approaches the x-axis as x decreases. What it looks like is a graph that runs along the x-axis and then crosses the y-axis and increases upward. It never actually crosses the x-axis. And they're saying here the function is continuous 1 to 1 and increasing. The domain is a set of all real numbers, which would be negative infinity to infinity. The x-axis is the asymptote of the graph. Okay, that means, and you know what an asymptote is? It's a line that a graph never touches. Okay, it can actually pass through in some rational functions that we'll be looking at in the future, but in this case, they'll never cross the asymptote. Okay, so it would never cross the x-axis, although it gets super, super, super close. The range is a set of all non-zero real numbers, so they would be positive numbers from 0 to infinity. And the graph contains the point 0, 1. So right here is your point 0, 1. I prefer to say that it would, if it's in the y equals a times b to the x, that see that this one's saying f of x equals just b to the x without an a value, that's why it's crossing at 0, 1. Okay, because you notice right here, that one doesn't have an a value. This is the y-intercept, though, if there is an a value other than 1. Okay, so if you end up with a number here, unlike this example, okay, this example is just basic parent function for all exponential growth functions. This graph has the intercept of 0, 1, because here a is 1. Okay, this is decreasing. A decreasing exponential function is where a is still positive, okay, and the b value, though, is between 0 and 1. So that would be things like 1/2, 1/3, 0.2, etc. Those are examples of values between 0 and 1. This graph is decreasing. Y decreases as x increases, and the graph approaches the x-axis as x increases this time. So an example what that would look like is a graph that's coming from high and then down through low. And again, for this example, the a value is 1. Therefore, the intercept here is 0, 1. That's what that looks like. It's got the same idea as far as the domain, negative infinity to infinity. The x-axis is the asymptote, which means it never touches that x-axis. Just a minute. The range is a set of, again, all positive real numbers, 0 to infinity. And the graph contains the point 0, 1. Remember, again, this has an a value of 1. Now we're going to classify each function as a exponential growth or an exponential decay. It's going increasing from left to right, therefore it is growth. The second one, it's coming down from left to right, so it's decay. I want to notice a couple other things about the equations. Do you see anything to do with the 1/2? Look at the graph and the equation and see what you can tell. See anything to do with the 1/2? It's the y-intercept. Yep. Okay, so your A is a 1/2. The B here is 3, which means it's stretching, its growth factor is 3. This one had an A of 1/2. This one, you could see that it's crossing at 0, 3 because A is 3. And 1/2 is between, the B value is 1/2, which makes it decay because 1/2 is between 0 and 1. Graph each function and classify it as exponential growth or decay. I want us to be able to identify and expect what we're going to get just by looking at the equation. If this format, again, is A times B to the X, in this case, the A is 1, okay, which means it should cross at 0, 1. Well, let's check if that's true. 2 to the 0 is 1, okay. The B value here is 2, which is greater than 1. So this should be growth. That makes, hope you get that, B value being greater than 1. So this is a growth. The rate of growth is 2. The y-intercept is 0, 1. The domain is negative infinity to infinity. And this graph should never touch the x-axis. So let's look at what it looks like, and then we'll finish writing these ideas. I'm going to substitute in -3 in for x and talk about what 2 to the -3 is. I want you to remember how to evaluate things without using the graphing calculator. Okay? I mean, obviously, you can type this in, and you can go to the table, but it's going to give you a bunch of decimals. Not that those are so bad, but I really need you to know how to evaluate this so that you will understand the inverse of exponential functions, which are logarithmic functions. Logarithms are a new thing that you've never heard of. We're going to be talking about those in this unit. So 2 to the -3, to rewrite that with a positive exponent, is 1 over 2 to the 3rd. And we've memorized that 2 to the 3rd is 8, so this is 1/8. So what's 2 to the -2? Well, it's 1 over 2 squared, which is 1/4. 2 to the -1 would be 1/2. 2 to the 0 is 1. 2 to the 1st is 2. 2 to the 2nd, 4. 2 to the 3rd, 8. So we got some nice points here to plot. I'm going to start the low ones, the high ones. 3, 8. You need minimum of 3 accurate points on your graphs. 2, 4. We did 0, 1, 1, 2. And then I could go backwards. -1, 1/2. -2, 1/4, etc. All right, so we just want to draw it as it's running along the x-axis, but not crossing it. And then coming up, going up, 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 and away. The range then is from 0, non-inclusive of 0, because it doesn't cross or touch the x-axis, up to infinity. Now, end behavior, which we discussed in polynomial functions, it's a little different here. What is the left side arrow actually trying to get to? What y value is it getting closer and closer to? 0. So the graph f of x is approaching 0 as x approaches negative infinity. It's trying and trying and trying to get to the x-axis, but never quite does. The concept is very strange as far as, here's an analogy to that to try to get you to understand this, not touching something or ever getting there. If I told you, you can go right now, you can go home right now. If you can get, just by going halfway to the door, every time you go halfway to the door and try to get out, will you ever get out? if you only go halfway each time. So you're never going to get there. So I could just say that to you, but you only can go halfway each time. Half the distance to the door each time. You'll never get out of the room. You'll have to stay there. So anyway, maybe that helps a little bit with the idea of trying to get there but never actually getting there. Oh, did I finish everything? No, I didn't do the right side. What's the right side's end behavior? Infinity. So f of x is approaching infinity as x approaches infinity. All right, number 4. This time we have y equals, this is the format, a times b to the x. But in this case, the a value again is 1, so it should cross at 0, 1. And the b value this time is 1/2. So that tells me it's between 0 and 1, therefore it's going to be decay. And my rate is 1/2, the b value. If I put in -3, I have 1/2 to the -3rd, which would be 2 to the +3rd. Remember, change that to fit and change the sign of the exponent. So the reciprocal of 1/2 is 2. 2 to the 3rd would be 8. If I do 1/2 to the -2, I get 2 to the 2nd, which is 4. And if I do 1/2 to the -1, that just flips it over to 2. Does the reciprocal. If I put in 1, I get 1/2. If I put in 2, I get 1/4. And if I put in 3, I get 1/8. So this time, -3/8, this graph is definitely coming down. -2, 4, -1, 2, 0, 1, 2, 1, 1/2 to 1/4. All right, so it's still coming down. And oops, every time this is actually a 1/2 growth factor. So it is doing the 1/2 the way to the door every time. Getting half, the values of y are cut in half each time you increase the x's by 1. The y-intercept is 0, 1 again. Domain's -infinity to infinity. And the range is from 0 to infinity, not including 0. How can we describe the end behavior of this graph? What's going on the left? Students? Is f of x pointing down? So you're talking about as x approaches -infinity. That's the part that's -infinity. The graph is actually going up. So it would be approaching, f of x would actually be approaching infinity as x approaches -infinity. Maybe you meant that, but you just said it a little different. Okay, so let's just kind of remember how a review from last semester. On the other side, f of x is trying to hit 0. It's trying to hit 0 on the right side as x approaches infinity. Okay, we gotta turn the page, I guess I'm hearing. Okay, I want to go as quickly as I can here. This first graph, if you notice, they all have 2 to the x in them, every one of these. Okay, everybody see it? The common part? 2 to the x, 2 to the x, 2 to the x, 2 to the x, 2 to the x. Okay, this is the parent graph. Right? Like I call it the parent graph because the others are variations of that graph. So if y equals 2 to the x, if I were to start doing some values in my head, if I put in 0 for x, 2 to the 0 would be 1. So 0, 1 is on the graph. 2 to the first is 2. 2 to the second is 4. 2, 4. 3, 2 to the third is 8. And if I went backwards, 2 to the -1 would be 1/2. And I'm just going to sketch it running along that asymptote that we already know about, the x-axis, and then coming on up on the right. So this is your parent graph. So I put it in red, and then I'm going to change color for the next ones. The second one is multiplying what values would change by twice as much. See what I'm saying? 2 times what? What values are affected by that 2? Not the x's, but the y's, because you're multiplying the parent graph by 2, and it's y equals. So those points are going to stretch vertically by 2 times. So if I did put in 0, now I have an a value of 2. So it's not going to cross at 1. It's going to cross at 2. And just plugging in a couple of numbers. 2 times 2 to the 0 was the one I just plotted. 2 times 2 to the first would be 4. So 1 4 is on the graph. 2 times 2 to the second would be 2 times 4, which is 8. 2, 8. Okay, so again, the points have stretched vertically. And so they're coming along this way, going up like that. So it squeezed it closer to the y-axis, but that's just because the y's are increasing twice as fast. Okay, and now they're going to increase 5 times as fast because 5 is the a value. The growth factor is still 2. This should cross at 0, 5. Okay, and I might just plug in, say one more. 2 to the first is 1. 5 times 2 is, 2 to the first is 2. 5 times 2 is 10. So 110 is another nice point on that graph. We got something going like this. Okay. Now I'm going to go and graph these with this -1 here. Now think about this. What's going to happen to the y values if you're going to multiply the parent graph by -1? Yep, they're going to flip over, right? They're going to change sign. The y's are going to change sign. So over here, -1 times 2 to the 0 is going to be -1. You're going to be crossing down here. So I don't know if I had another color. Let's see. Oh, I didn't use blue yet, so I'll do this one in blue. You don't have to put these in color. I just thought it was helpful for my notes. -1 times 2 to the 0 would be -1. -1 times 2 to the first would be -2. So if I put in 1 for x, I'm going to get -2 for y. If I put in 2 for x, I will get 4, -4. 2, -4 is the point on the graph. All right, so we can sketch it now. It's going to run under the x-axis and go down. Okay, and then -3 times 2 to the x, that will give us a y-intercept of 0, -3. And then that's going to be coming down. If I put in 1, that would be -6. So that's enough right there, just to get a picture of what's happening to the graph. Okay, so I got them all graphed. What has happened? Okay, we found out that A is the y-intercept. Another way to put that is it is the original amount. Because we're going to be getting into some word problems and applications of this stuff. Describe the effect on the graph if A is positive. Well, then the graph is stretched vertically. So it's either stretched or maybe even flattened, it could be. Now, what happened when A was negative? It reflects the graph over the x-axis. So it then becomes not growth, but decay. Okay, it's decreasing from left to right. Does anybody still need this page? Okay. Graph the functions. All right, so what I see here is A is 1/2. I see B is 3. You just want to keep on identifying those pieces. So the y-intercept is 0, 1/2. The growth or decay rate, this one happens to be, is this growth or decay? Okay, just because there's a fraction for the A value will not create decay. It's the B value you want to look at. Okay, so the B here is larger than 1, so this is growth. The growth rate is 3. The domain's negative infinity to infinity, and the range is 0 to infinity. Yes. No. Will the domain and range, the question was, will the domain and range always be this? If they're in the strict form y equals a times b to the x, it depends on if a is negative, because remember then it reflects it over the x-axis. That would affect the range, not the domain. The domain's going to be negative infinity to infinity always, but the range can vary. And they're also going to be shifts that we're going to talk about in a few minutes, okay? So I want to say that always. Sometimes we want to look at it. These were the first basic ones, and those would be that if they're y equals a times b to the x with a being positive, okay? All right, so I put in -3. Oh, my goodness, that's going to be kind of gross. Anybody go in the grapher yet? Because these are icky decimals. You may go in the grapher if you'd like, go into your table and get these values. And I'm just going to tell you what they are for time's sake. So if you'd like to go look, you may, of course, do so. This would be 0.02. The next one's 0.06. Then 0.17. I'm doing to the 100th place, please. If you put in 0, you get the 1/2, or 0.5. If you put in 1, you're going to get 3/2, or 1.5. If you put in 2, you're going to get 9/2, or 4.5. And 3 would give you 13.5. 27/2. Okay, so I need to just sketch or try to plot at least a couple of points that I prefer to get 3 accurate ones, but this one's not lending itself to anything very nice. 1, 1.5 is pretty good though. And then 3, 4.5, that's not bad. So we got 3 decent ones right there. Oops. Did I do something wrong? I put 3, oh, I sure did. Thank you. 2, 4.5. I missed my mark. Thanks for noticing. And I can't really fit the 13.5. I probably did it because I wrote kind of goofy on my chart. Okay, so we're running along the, oops, I somehow went under it. Stay above. And that would be the graph. And the end behavior, f of x is approaching 0 as x approaches negative infinity, and f of x is approaching infinity as x approaches infinity. I didn't have end behavior on the last one. I was just double checking if I'd forgotten something. Okay, now I think we're going to be looking at shifts. Let's see what's next. Oh, not yet. Now, if you have an exponent as negative x, you want to rewrite this. 3 times, I am going to apply the negative sign to the 4. Okay, the reason being, I want the x to be an exponential form. I want to be able to identify the a value. A is 3. What is b? No, it's not 4, unfortunately. And it's not -4. What does the exponent of -1 do to it? 4 to the -1 is 1/4. So B here is actually 1/4. And you are going to need to know how to describe why this is now actually a decay problem. The B value is not 4. The B value or growth rate, or sorry, this is not a growth, this is a decay. The y-intercept is 0.3. The decay rate is 1/4. Okay, so the number should be coming down. The domain's still negative infinity to infinity, and the range is going to be 0 to infinity. Well, let's see what's happening. Because, like, if you put in -3, if you think about it, even into the original function, you would have 3 times 4 to the third. That's 3 times 64. These numbers are kind of big. So it's actually 192. 3 times 64 is 192. Your next one, if you put in -2 in here, you'd have 3 times 4 to the positive second power would be 3 times 16, which is 48. If you put in -1, you'd have 3 times 4, which is 12. If you put in 0, you'd get 3. If you put in 1, you're going to have 3 times the fourth, which is 3/4. And if you put in 2, you're going to get even smaller. So it'd be 3/16 and then 3/64. Now, if you want the decimals, this is 3/4, of course, 0.75, which you can get off your graphing calculator. 0.19 is the approximation for that. And then 0.05 is the approximation for 3/64. We can't plot a whole lot on here. We can't even really get to -112. So if I estimate, that's up there somewhere. 0.3, 1/3. That's all I'm going to actually show. Way up there and then through. Don't cross the x-axis. And then, even though I just look like I did. Your grapher, you'll barely be able to tell that the graph even extends along there, especially on an older model. All right, so the end behavior, f of x, the graph, is pointing up to infinity as x approaches negative infinity. And on the right side, the graph is trying to get to 0 as x approaches infinity. Okay, anybody still need this? No. Okay. All right, so we should have A is 5 in this case, so 0, 5 should be on my graph. This is 1/3 to the positive x power, which is going to be decay because B is between 0 and 1. So the decay rate is 1/3. All right, the y-intercept, 0, 5. Domain, negative infinity to infinity. Plot 0, 5. And then let's get some more stuff. All right, I'll go ahead and help out with these values. If you put this into the grapher, you'd be having 135 for that one. It's actually going to be 5 times 27. Put in -2, that'd flip it over and square it, so you'd be 5 times 9. This should be 45. Then 5 times 3 for the next one, which is 15. 0, 5, and putting in 1, you'd get 5/3. Putting in 2, you'd get 5/9. Putting in 3, 5/27. And of course, those are little decimals. If you want the decimals, it's 0.19 for the last one, 0.56 for the second to last one, and 1.67 for the third to last one. All right, we can plot little on this that looks good. Let's see, 1.67. And then, I guess -115 you can't really plot because it's way up there. But if I did plot 2, 5/9, that's pretty close to a half. So good enough. end behavior, f of x is approaching infinity as x approaches negative infinity. And f of x is trying to get to 0, approaching 0 on the right as x approaches infinity. Oh, don't know why I forgot it. 0 to infinity. Forgot to write the range down. Okay. 8. 4 times 2 to the x. We've got a is 4, b is 2. So this should be growth with 0, 4 as your y-intercept. Growth rate of 2. Domain negative infinity to infinity, and the range 0 to infinity. Okay. This is number 8. So if you put in negative 3, 4 times 2 to the negative 3 is going to be 4 times 1 over 2 to the third, which is 8. That's actually going to give you 1/2. And of course, you can use 0.5. If you put in negative 2, you're going to get 1. If we put in negative 1, 4 times 1/2 would be 2. If you put in 0, 4 times 1 would be 4. Put in 1, 8, 2, you get 16. And then if you put in 3, you'd get 32. Okay, negative 3, 1/2. Negative 2, 1. Negative 1, 2. 0, 4, and 1, 8. All right, the end behavior, f of x is approaching 0 as x approaches negative infinity, and f of x is approaching infinity as x approaches infinity. Okay, now let's see if we can apply some previous knowledge. A general exponential function, y equals a times b to the x minus h plus k, translates the graph of y equals a times b to the x horizontally h units and vertically k units. Okay, so this graph would be the graph of this, except it has been shifted. Down 4 is one part. What about horizontally? H always does it. Remember? Okay, let's remind ourselves. It's y equals a times x minus h quantity squared plus k, where hk was the vertex. All right, the h was your horizontal shift. The k was your vertical shift. So in this case, it's still the same exact idea. So what does this minus 1 do, Ariana? Lucas, what's the minus 1 do? Okay, I suggest we focus up here because that's not what I was looking for. Okay, shift horizontally, right 1. And vertically, that 4 shifts it down 4. Okay, now I'm going to graph this parent graph. This would be the parent. I'm going to plug in some numbers. Maybe just start with negative 1. That would give me 3 times 1/2. So that'd be 3 halves. If I put in 0, I'll have 3 times 1, which is 3. If I put in 1, I'll have 3 times 2, which is 6. Now, I just got 3 nice points. And the next one's kind of big, so if I put in 2, I'd have 3 times 4, which is 12. All right, my point was, these are ways to get, this is how I could get that parent graph graphed. So I'm going to graph it right now. and then I'm going to dash it because it's not the answer that I actually want in this picture. So negative 1, 1.5, 0, 3, 1, 6, and I'm doing this because there's something in the book assignment in this section that this is like one of the only real decent ways to do the problem, okay? It makes a lot easier to do. 212, it can't really fit on there, but something like that. So I'm going to dash this because it's not the answer. But I'm going to use these key points that I plotted. Okay? And I'm going to graph this one. Now, you can go in the grapher. You can get this out of the table. And I'm not even going to write these down right now. Because what I'm going to do is graph it without that. I'm going to do it using the shift. So, ready? What's the shift? Horizontally, right 1, vertically, down 4. So I take this point. I go right 1 and down 1, 2, 3, 4. I'm going to take this y-intercept point and translate it right 1, down 1, 2, 3, 4. I'm going to take this point that is at 1, negative 1, 1.5, and I'm going to go right 1 and down 1, 2, 3, 4. It's at negative 2.5. Now, here's the tricky part. How did the asymptote move? Yeah, you don't have to move. You don't have to do right or left on an asymptote. But which way would it go if it's a horizontal line? It would slide up or down vertically. The asymptote has to come down. Okay? So because asymptote was y equals 0, it's not at y equals 0 anymore. It's moved to negative 4, the k value. So I have to dash in a line here. You're going to have to dash it and show me that you know exactly where the asymptote is supposed to be. Your graphing calculator will not show you that line. It'll give you a picture of what it looks like. All right, so I'm just going to sketch it now. And then you can verify these values in your grapher. But if I put in, I'll tell you what they are when I did go into the graphing calculator. This was negative 3.8, negative 3.6, negative 3.25, and then negative 2.5, and negative 1, 2, and then 8. Okay. We have 2, 2 in our graph. I'm just going to start looking at some of these points. 3, 8. We didn't plot that one because we didn't actually have, if we went right 1 down 3, that was where this one would have been. 3, 8. So I kind of missed a little bit. It goes up more like that. But if you verify these, 1, negative 1. Oh, sure, there it is. 2, 2. Oh, yep, that's one of the ones we shifted. And 0, negative 2.5. Yep, that's right there. So it actually is easier to shift. Okay, so what's the domain? Still negative infinity to infinity. But here's where, when you were asking me that question before, the range changed, didn't it? So it goes from negative 4 to infinity and does include the negative 4. Okay, so that makes more sense now, I hope. All right, so the asymptote shifts whatever the vertical change is. Take the shift in the following functions. What's the shift going to be here? This will be a vertical down 3. Domain will be negative infinity to infinity, but what changed is the range. So that's going to be negative 3 to infinity now. So the next one, we got 3/4. That's a decay. okay? The shift is a h value of 1. It's minus 1, so that would be not left, but right. So this would be a horizontal shift of right 1. Domain's still going to be negative infinity to infinity. If you only shift right, does that change the asymptote? No, so it's going to be 0 to infinity for the range. Okay, the next one, 9 to the x transformed to 9 to the x plus 1 minus 2. The shift is horizontally left 1 and vertically down 2. The domain is still negative infinity to infinity, but the range did change because it went down. It went down to negative 2 to infinity. I don't know why we didn't have one where the shift was up on the asymptote. Okay, we will talk tomorrow about applications of real life exponential growth and decay. Have a nice evening.